So 15.5 part 2. So today we're going to do normal vectors and area with parametric surfaces. So in chapter 14.5, we came up with a method for using a double integral to find the surface area of a surface. So if we have our surface was given by z equals f of xy, we said that the area, surface area, S was the double integral over our region of ds. And we made an argument using cross products of partial derivatives to come up with an expression for ds. We said that ds, our surface area element, our little element of area, was the square root of partial with respect to x squared plus the partial with respect to y squared plus 1 dA. And if we remember, what we did was we looked at a little piece of the surface and we came up with tangent vectors to the surface in the x direction and the y direction, and took the cross product of those tangent vectors, and that approximated the area of a little parallelogram, and took the size of the little parallelogram smaller and smaller, and we came up with this expression for ds. We're going to do the same thing for a parametric surface. So what we're looking at is we have our coordinate axes, and this is our x, y, and z. And we have some surface that's represented parametrically. And we're looking at our parameters are u and v, like we talked about yesterday. And we're looking at tangent vectors. We're taking the partial with respect to u as a tangent vector in one direction, and a partial with respect to v as a tangent vector in the other direction. And we end up with, we also have a normal vector at this point on our surface. So we're going along the curve, on the surface in the direction of u, our parameter u, and in the direction of our parameter v, and looking at these tangent vectors at this point. And we're going to go through the same argument. I'm not going to do the entire argument because it's really the same thing. This is what we're talking about here. So let's look at a little piece of this surface. So we have we're breaking our surface into little rectangles. The sides of our rectangles are parallel to the u-axis and the v-axis rather than the x-axis and the y-axis, because we're parameterizing our surface in terms of u and v. So here's one little rectangle, or a parallelogram, I guess, but I'll call it a rectangle. So we're magnifying this a little bit. So here is our little piece of surface. We're looking at a point here, and we're taking a partial derivative with respect to v is going to be tangent vector in one direction, partial derivative with respect to u in the other direction. And we're looking at a small change, delta u, in this direction, and a small change, delta v, in this direction. So these partial derivatives, these vectors, are tangent vectors to a point on the surface, and our normal vector is going to be given by the cross product of these two vectors. So that's going to be normal to our surface. And using the argument that we used in chapter 14.5, if we let delta U and delta V become very small, the area, the magnitude of our normal vector, the magnitude of RU cross R sub V, is the area of a small parallelogram. If we let that delta U and delta V get smaller and smaller, that cross product approximates the area of a little rectangle better and better. So the little piece of area we said was approximately the magnitude of this cross product times delta U, delta V. So when we form the cross product, that area is approximately this quantity. We let delta U and delta V get very, very small, and we take the limit. We're taking the limit as delta U and delta V go to 0. And we sum these small areas over the surface to get our surface, the surface area of our parametric surface. And we get an expression for the area of our parametric surface. The area A is going to be the double integral over our region of the magnitude of R sub U cross R sub B du dv. And the magnitude of R sub U cross R sub V is the magnitude of the normal vector. So we could also write that as the magnitude of n du dv. So there's an expression for the surface area of a parametric surface. Same argument that we used to find the surface area of a surface represented in rectangular coordinates. Now we just have it represented in terms of our parameter. Everybody good with what we're doing there? Kind of the argument that we're using should be kind of familiar by now. We've done it several times, similar arguments several times. If we have our surface represented in terms of rectangular coordinates, so if we have z equals f of x, y, then our position vector, our parametric representation of our surface is xi, we talked about this yesterday, plus yj plus f of x, y, k. That's a parametric representation of the surface. The surface area integral reduces to exactly what we came up with before. So if we represent our surface in rectangular coordinates, this would be the parametric representation, and our surface area integral comes out exactly the same.
What's the other function that you cross with y? That you do doing that?
So we would cross r sub x with r sub y. Partial derivative of this with respect to x, the partial derivative of this with respect to y, and that would be our cross product. And when we do the magnitude of that cross product, we get this. Okay? And we're assuming, what we're assuming with this entire argument is that our surface is smooth. And what that means is that R sub u cross R sub v is not 0 on the surface. So we have a smooth surface. So we're talking about a well-behaved surface. So this lets us do some work with parametric surfaces. We can find tangent planes, and now we know how to find surface areas of surfaces represented parametrically. So yesterday we practiced with parametric representations of surfaces. Now we can do some calculations with them. What we're going to do now is take this in the next section that we'll talk about tomorrow, and we are going to do surface integrals. The surface integrals are like line integrals. We're going to sum some function over a surface. And now we have a way to do that because we know how to do this integral on the surface. So any questions on the development, what we're talking about? All right, so what I wanted to do today is just do a couple of examples of calculating doing some of these calculations with parametric surfaces. So we'll find a tangent plane, and we will find a surface area. So for our first example, so we want to find an equation of the tangent plane to, and we have this parametric surface, R of u and v. So here's our surface, and we want the equation of the tangent plane to this surface at the point 1, 1, 1. So what do we need to write our equation of our tangent plane? We need a normal vector, and we find the normal vector we just decided by finding our partial derivatives, right? So we need to calculate R sub u. So what is R sub u going to be? I'll start us out. I. No j. So I'm just going to write 0. J. And then what do we get for our k component? 1/2. What is it? 1/2 v. Over square root of uv. Right? Everybody agree? Yes? Okay. R sub v. Does this quantity look familiar? Where did we calculate a partial derivative like that? On the take-home, right? When we just calculate our Jacobian. All right, so
It's still early.
what's that?
It's still early.
It's still R sub v. So what do we get for R sub v?
0.
0 I hat plus
J.
j hat. That one's easy. Plus, and we're symmetrical, so we just kind of switch things around a little bit. 1/2 u over square root of uvk. So for our normal vector, we need to make a cross product. So our normal vector is going to be given by R sub u cross R sub v. So I'll write out this determinant. I always have to write these out. I don't know how you guys can calculate these without writing this out. It's always impressive to me. Yeah, I have to do it this way, or I mess up. I always mess up signs. just mess in general. That happens with cross products. I think that's the most common mistake with cross product, is getting signs wrong. So when we make this cross product, I'm not going to write out all the steps, but we end up with minus v over 2uv square root I minus u over 2 square root uvj plus k. And then we want that at 1, 1, 1. So at our point that we're interested in, we plug in 1, 1, 1. We get our normal vector is minus 1/2 I hat minus 1/2 j hat plus k hat. So our direction numbers, this gives us our direction numbers for our equation of our plane. So A is negative 1/2, B is negative 1/2, and C is 1. So our equation for the plane is going to be minus 1/2, and we know we're 1, 1, 1 is on our surface. So minus 1/2 x minus 1 minus 1/2 y minus 1 plus z minus 1 equals 0. Or we could rewrite that if we distribute everything and simplify. We get x plus y minus 2z equals 0. So that's our tangent plane at 1, 1, 1. Find the cross product to get our normal vector. Cross product of our partial derivatives to get our normal vector. Normal vector gives us our direction numbers. And what we're going to be doing when we start talking about surface integrals, if we have our function represented in terms of x, y, and z, what's a nice convenient way to find our normal vector? That's in the plane. So think back all of our lovely things that we did with vectors. How do we find a normal vector to a surface? Del, the gradient. There we go. A gradient. So if we have f of x, y, z as a constant, we can take the gradient and find our normal vector. So the gradient is going to make a comeback in chapter 15 to find normal vectors, because normal vectors are going to be really important when we're working with surfaces.
The gradient is the normal vector, right?
Right. If we have f of x, y, z equals a constant, the gradient is a normal vector.
And it's just the partial derivative.
And that's just our partial derivatives. Partial with respect to x, partial with respect to y, partial with respect to z. Isn't that nice how the parametric surfaces kind of interconnect with what we've talked about already? And it all makes...
It almost seems like design.
It all fits together, makes nice sense. All right. See, we had a few drinks of Tranya earlier in the semester, and now it's all coming back, and it's got a nice blend of Tranya and some other parts of our meal, and it's all going to come together and be a lovely banquet. All right. Let's find the surface area of a nice parametric surface. We actually get to do an integral now. So we're going to find the surface area of this parametric surface R of u and v, which is square root of u cosine v I plus the square root of u sine v j plus u k hat. And we have 0 less than or equal to u less than or equal to 4, and 0 less than or equal to v less than or equal to 2 pi. All right, so we need to find our surface area. I was just thinking about what the surface would look like.
Like that problem 25.
I think it's like that problem 25 yesterday. I think so. I think this would just be a cylinder, right?
Yeah, it would be
But it goes like this.
No, because this gives us a disk in the xy plane, right? And the radius goes from 0 to 2, and then z goes from 0 to 4. I think this is just a cylinder. All right, so we are going to find, but we're going to do it the fun way, not the geometry way. We need to find this quantity, r sub u cross r sub v, magnitude, du dv. So this is our integral that we're going to evaluate. So we need to calculate these partial derivatives and form our cross product. So r sub u, what is r sub u going to be? We get a nice expression for r sub u. What's our partial with respect to u here? I'll start us out. Cosine v over 2 square root u I hat plus, and this should be, this is a v here. So sine v over 2 square root u again, j hat plus k hat. R sub v minus square root u sine v I hat plus square root u cosine v j hat and 0 k hat. So now we can do our cross product to get this quantity here. So r sub u cross r sub v is ijk. Cosine v over 2 square root u sine v over 2 square root u 1 minus square root u sine v square root u cosine v and 0. When I do this cross product, I'm not going to write the intermediate steps, but when I do it and simplify it, I get minus square root u cosine v I hat minus square root u sine v j hat plus 1/2 k hat.
Should it be plus?
No.
Okay.
Did I?
So you're good.
Yeah.
We're good? Okay. I'm pretty sure that one's right. All right, so there's our cross product. Now we need to find the magnitude of this. So the magnitude of r sub u cross r sub v is going to be the square root of u cosine squared v plus u sine squared v plus 1/4. And this simplifies, so it's not quite as messy as it would seem. We get square root of u plus 1/4. So not too bad. So now we can write our integral, our double integral. So we end up with our surface area is the integral over our region of the square root of u plus 1/4 du dv. And our limits are nice and easy, 0 to 2 pi, 0 to 4 of the square root of u plus 1/4 du dv. Let's see. We would, yeah, because each of these is constant. So neither of our limits of integration are functions. So we could switch the order and it would be fine. So we can integrate this. This is not a difficult one to evaluate. When we evaluate this, we end up with pi over 6 times 17 square root 17 minus 1. Or approximately 36.177 square units. And so what would we get if we would this agree with what we would get using geometry? If we're thinking about this the right way? Right. I have to look at that. It makes me curious. It makes me curious if yeah. Any questions? Any questions? All right, so that's all I wanted to do today. So our homework. There you go.